Hello, my name is Stefan and I will present you today the paper entitled A Generative Semi-Supervised Classifier for Datasets with Unknown Classes for the ACM Symposium on Applied Computing 2020. My talk will be about classification problems, and one of the best known datasets for multi-class classification is the handwritten digit database MNIST, which you can see on the left-hand side of this slide. In this dataset we have a total number of 10 classes, and we have different samples of all these classes, and this is a usual setup as we know it from classification problems in machine learning, at least according to the theory. Because what we investigated in our research is a problem which is practical, and sometimes in practice the setup looks a little bit different. For example, like the one on the right hand side of this slide. Here you can see that we have only some of the classes that are known in advance. So we have only 0, 2, 5, 8 and 9, which are known classes and which are classes that we have in our labeled training dataset. On the other hand, we have a lot of different samples from the known or even some other classes that are unknown in advance. And for these elements, we do not know what their real class is. And of course, these kind of unlabeled data, they are present in a very large number. But it's very hard in practice to get labeled training data which are reliably labeled. And this is especially what is a practical problem that we are aiming to solve in this paper. So the problem, as I said, is linked to classification, and we restrict ourselves to semi-supervised classification, which means that we have a labeled as well as an unlabeled training dataset. To make this problem even more challenging, we are investigating datasets with unknown classes, which means that we have a labeled training dataset with known classes as well as an unlabeled training dataset with known and unknown samples. And finally, we would like to investigate this problem in a generative way. I will come back to that later. But generative means that we understand a lot more on the distribution of the data. Okay, in order to start with the mathematical formulation of the problem, let's talk about multi-class classification. Multi-class classification means that we are interested in identifying a mapping F from a feature space. The feature space in our case will be continuous, but we can also think of a discrete feature space as well. From F to the number of classes or the set of classes. Classes will be C1 to Cn in our case. So we want to identify the class of a feature vector from F. In order to investigate semi-supervised problems, we have to take a closer look on the training data. In particular, we have two types of training data. On the one hand, we have L, the labeled training data, which means that for these training data we have both the feature vector as well as the ground truth on the class label available. On the other hand, we have D, which represents the unlabeled training data, where we only know the feature vectors. For unknown classes, this is a little bit different. So we are now investigating the case that C is just the set of known classes, which means the set of those classes that are represented in our labeled training dataset. On the other hand, we have C+, which denotes the whole set of classes, which consists of C, C1 to Cn, as well as the unknown classes Cn plus 1 to Cn plus k, which are not represented in our labeled training data, but rather just in our unlabeled training data. So we do not know which of the unlabeled training data are unknown classes. We are now interested in defining a classifier which maps from the feature space to C sub 0, which means that we want to identify whether an element is from either one of the n known classes or from any of the unknown classes n plus 1 to n plus k, which are denoted as 0. Now, what makes a classifier generative? Generative classifiers are classifiers that describe a probabilistic model on the generating process of the data given the class C. Therefore, we are understanding how the probability distribution of the data within a class is, and this is of course more information than if we just obtain the class label. And therefore, generative models give us a more insight into the data distribution, but on the other hand, for them it might be more difficult to distinguish between known and unknown classes. This is why problems with unknown classes are usually tackled in a discriminative way. So what is the concept? Back to the whole overview picture, we have here, for example, 3 classes that are known, as well as elements from other classes that are just unknown a priori. And further, we have unlabeled and labeled training data, where the labeled samples are just from each of the known classes, while the unlabeled data are both from the unknown classes as well as from the known ones. How can we tackle such a problem now? One possibility to tackle a probabilistic model is the Bayesian formulation, and we will use Bayesian decision theory. In particular, we will minimize the risk, or the loss function times the likelihood times the prior, so loss function times the posterior probability of each class. In particular, we are interested in minimizing the risk function, of course, and we sum over all possible classes that X, our data, might belong to. Our loss function tells us how big is the loss if we select the label or class C, and the underlying ground truth class is C tilde. And we can simplify this by using just the 0-1 loss, which means that we have loss 0 if we select the right one, the right class, and 1 if we select the wrong class. And in this case, the formula gets much easier. So we are just looking at the class C star, which is the maximum over the likelihood, so probability of the data given the class, times the prior of the class. So how will we model likelihood and prior now? In our case, we will, for reasons of simplicity, denote the likelihood as a Gaussian distribution for each class, and we will estimate the priors, the prior probabilities as the proportions of the known classes in the training data, in the label training data. So this would already solve a lot of the problem, and this is also quite an easy kind of classifier that some of you might recognize, because this is somehow like the Gaussian naive Bayes. But there are two differences that I would like to point out at this point. First, we do not know how to estimate the likelihood given the class 0, so given an unknown class, and we do not know how to set the prior of this unknown class yet. This will be the major part of the algorithm we will present in this paper. And the second thing, we do not necessarily restrict to independent features, which is also something that is usually done in the Bayesian or naive Bayes classifier. So therefore we are open for any kind of Bayesian modeling as well. So the main question is now how to select the likelihood of the data given the unknown class and the prior of the unknown class, or in our case it can also be multiple unknown classes that are just aggregated to 0. We will use a two-step approach for this purpose. Step 1 will be to use the so-called SEM algorithm introduced by Liu et al. And this algorithm is used in order to identify so-called likely unknowns within the unlabeled training data. These likely unknowns are the black elements here, which is a subset of elements from the unlabeled training data that are very unlikely to originate from the known classes C1 to C3. Further, we have a second step, and this is to model these black elements, these likely unknowns, with a Gaussian mixture model, because each of the known classes has one single Gaussian distribution as an assumption, and therefore we will assume that also the unknown classes are of the same type, and since we do not know how many unknown classes we have, we will just use a Gaussian mixture model for them. Okay, step 1, detecting likely unknowns. A likely unknown, or the set of likely unknowns, is a subset of D of the unlabeled training data, which is suspected to originate from unknown classes. How do we obtain them? The SEM algorithm is usually used for binary problems, so we used an adaptation that we made for the multi-class case. We sample a subset S of L, which is the set of labeled elements. So we get some so-called spies, and these spies will be used in order to identify which of the unlabeled elements are from unknown classes. And we add these elements to the unlabeled data D, and we initialize all elements from L except for those in S with their real classes. We know them because they are in the labeled training data. And we initialize all elements from D as well as those from S with class 0, denoting unknown. And then we run an EM algorithm to train a naive Bayes or a more general Bayes classifier Q to identify classes C1 to Cn as well as 0. And by this modeling, we obtain a set U of likely unknowns, which is defined as those elements in the unlabeled training data which have a lower likelihood given the known classes than the minimum of the likelihood of all spy elements given their ground truth class. So in fact, using this minimum as a threshold, we can identify which of the elements in D are most likely not from any of the known classes. Now we can obtain the prior for this class 0 or for the unknown classes by counting the number of likely unknowns divided by the whole size of the unlabeled data. Next step is to fit a mixture model. And with this mixture model, we have the assumption that U originates from equally weighted mixture, from an equally weighted mixture of Gaussians, which means that U represents multiple unknown classes, Cn plus 1 to Cn plus k. And since each of the known classes is represented by a Gaussian distribution, we also assume that each of the unknown classes is represented by a Gaussian distribution, and therefore we use a mixture model for the aggregation of all the unknown classes. This will be used then to estimate the probability of x given 0, which is the likelihood given the unknown class 0. And this is just the likelihood or the density function of the mixture model with L mixture components, and we can estimate mu I and sigma I from the likely unknowns, which would be easy. The problem here is that in order to estimate the parameters of a Gaussian mixture model, we have to know how many mixture components we would like to model. And for this purpose, we use the so-called Bayesian information criterion, taking both the labeled as well as the unlabeled data and the known as well as the unknown classes into account. And the big here is the number of parameters minus the likelihood, where the likelihood is calculated always over the best set of parameters for each of for a fixed number of L components. And the classifier that we calculate the big for consists of both the probability or the likelihood of the known classes as well as the likelihood of the unknown classes. So now we have obtained all the ingredients we need in order to build our classifier. So we will evaluate it on some experiments. We will use multi-class classification datasets with more than 3 classes, for example, from the UCI datasets. We will use a random partition into n known and k unknown classes, where n plus k is always the total number of classes of each dataset. Further, we will evaluate the experiments with the F1 score. F1 is the harmonic mean between the precision and the recall, and macro-averaging means that we average over all the known classes. We will test our semi-supervised classifier with unknown classes as a CUC against the following state-of-the-art approaches. On the one hand, we have 2 different classification approaches, the EL, the exploratory learning, as well as the SEM, which can also be generalized to a multi-class setup directly. And on the other hand, we have 2 different clustering approaches, because also semi-supervised clustering is able to solve similar problems with the unknown classes. Let's take a look at the results. We have results for 3 different setups. On the one hand, we have n equals to 2, which means that we have just 2 known classes and all the rest are unknown. On the other hand, we have n equal to k, which means about 50% of known and 50% of unknown classes. And we have got k equal to 1, which means that only 1 class is unknown and all the others are known. We are looking at different datasets, and we see that especially as a CUC obtains very good values, as well as the SEM, where of course SEM is one part of SSCUC, which explains that both behave similarly in many datasets. Since some of the datasets just have 3 classes, the n equal to 2 case is the same as the n equal to k and k equal to 1, and therefore the last columns of some of the rows are empty. Further, we should note that our classifier is a generative classifier, whereas, for example, the CECIB classifier is a discriminative one and therefore provides us less information on our data distribution. What is the application we are applying this method for, or we developed this method for? This was in semiconductor industry, where we would like to classify different sources of deviation within spatial patterns. And we have a semiconductor product, a so-called wafer, which is on the one hand previously affected by previously known error patterns or classes, for example some kind of ring, some spot, some gradient over the whole wafer, or which might be affected by an unknown error pattern which we do not know a priori, and this is exactly the setup that we were discussing in this paper. So finally, what we saw was that unknown classes make classification a quite challenging problem. that we can solve with the algorithm we presented. On the other hand, we see that generative classifiers, of course, have more explanatory power, although they might have more difficulties to explain the differences between classes. Further, we have a low parameter sensitivity in our algorithm, and we have a good performance, especially with few label training data, which is a very challenging setup in this area. Of course, there are limitations, and in our case, the limitations are in particular if we have a very high dimensional feature space. And we have the possibility to adapt our algorithm also to other probability distributions and setups. Thank you for your attention.